Hello, good evening. Tonight is the third talk in the G-Research lecture series. This lecture series features experts in science and technology speaking on topics in which they're recognized thought leaders. This time round, the topic is artificial intelligence, and it is my pleasure to introduce Professor Michael Jordan to speak to us tonight. Professor Jordan is one of the most influential people in the field of machine learning. He is professor at UC Berkeley, split between the Department of Electrical Engineering and Computer Science and the Department of Statistics. He was previously a professor at MIT. He is a member of the National Academy of Sciences and the National Academy of Engineering, and has many awards and honors, which I don't have time to talk about today. However, I would like to point out that back in 2016, there was a big analysis of the published literature by the Semantic Scholar Project, and he was found to be the most influential computer scientist. Professor Jordan has also had great impact through his teaching. The list of his past students includes people like Andrew Ng and Zubin Garamani and other world-renowned scientists. He is also really well known for the breadth of his research. Now, we're a diverse group at G-Research, so I think it is really great that we're going to be hearing from someone who has been really important in bringing together fields, in particular computer science and statistics and engineering, to make real impact in machine learning. After the talk, we'll ask Michael some of your questions. You should find a card with a link to the app on your chair. So if you have any questions during the talk, put them in the app, and we will put as many as we can to Michael at the end. Finally, there will be canapes and drinks after the talk, so please do join us for that. And that's all from me, so now would you please give a warm welcome to Michael Jordan.
Thank you very much. It's a pleasure to be here. Thanks for coming out of the evening. I can't believe so many people don't have better things to do in the evening. So I'm glad that I'm now onto my slides and I don't have to keep seeing that picture of myself. That was taken at 8 a.m. when I had just returned from a trip from Europe, and I was jet-lagged and haggard, and awful picture. So this is going to be hopefully intellectual entertainment. It is a challenging topic to try to say something about. I was trying to think about historical junctures that are maybe relevant, like the steam engine was invented. What does that mean for everybody? And let's think that through a little bit. It may be that kind of level of change. On the other hand, it's being hyped way, way too much. There's expectations which are not going to be met, and so we have to think about that as well. I don't know if that was true about the steam engine, but I bet you it was as well. So just a couple of anecdotes before I start going through some slides. First of all, I gave a presentation, this kind of material, not long ago in New York City to a quantitative finance firm. And the founder came up, wanted to talk to me afterward, and we went to his office. And I thought he was going to sort of say, what's the implications of this for my business? You know, how can I make money off of this? Where's this all going? And he said, no, what I really want to ask you is, what should I be telling my children to study in college? All right, so that's really kind of interesting. That's very much part of this, that things have accelerated. You know, I think in the steam engine, in that era when there was a technological change, you had 30 years to kind of adapt to it. So people could retire and the next generation could be ready to go. And it's much faster now. So all of you probably have found your way into nice jobs and succeeded. But when you're 40 or 50, you know, it's going to be a challenge to keep up. And what should your children do? So the other anecdote I wanted to mention was I was at the Newton Institute today in Cambridge, gave a talk there, and there's a beautiful portrait of Isaac Newton there on the wall. And I was talking about gradient methods and symplectic geometry, sort of things that he had invented. So it was quite interesting to be giving the talk there. And I was thinking about how the methods that we're calling artificial intelligence are really not that sophisticated. They are gradient descent. They are mathematically things that Newton would definitely recognize and you know, not be that surprised by at some level. But I thought about how our technology has moved so fast, and I have the cell phone in my pocket, and I thought about this, and I thought about showing this to Newton. right? And first of all, it has lights coming out of it. And Newton spent his life, with prisms, trying to think about how light got split up and all. And the idea that a little black object like this could create light of all spectra, he would find completely mysterious. The fact that it could have a voice could come out of it, completely mysterious. And of course, the fact that I could talk to someone in a distant part of the world, completely mysterious. My children don't find that mysterious, but he would. In some ways, I'm going to be talking on two fronts. One is this technology is not so revolutionary. It's not that big a deal. It's just a natural next evolution of statistical thinking. On the other hand, it will probably have a very big effect on technology and human lives. And so it's an interesting topic to be thinking about. Okay, so first of all, I don't usually use the term artificial intelligence myself in my own research. I'm a statistician first and foremost. I think the problem of inference, taking incomplete observations of the world and using that as a basis for action, that to me is one of the interesting intellectual problems of all times. It's sort of 300 years old in a somewhat formal sense. And computer science is a much younger discipline, and it's also interesting, but I think inference is really the key thing. And if you're in the finance industry, that's what you do. You take partial information about the microeconomic state of the world, and from that you want to say something about what's going to happen, tomorrow or next month. And you're doing that kind of inference, but my child does that too as they walk around an environment and try to figure out what's going to happen in that environment and what they should do. So I don't call it AI, I call it statistics, but this word machine learning came around in about 1980. It came around because computer scientists didn't know anything about statistics. Our fields had gotten separated, and they thought, wouldn't it be interesting if you could get a computer to learn from data? Wouldn't that be novel? Wouldn't that be exciting? And so they started writing down procedures to allow that to happen and created things like decision trees and nearest neighbor and eventually things like neural nets. All of these things had been already created in the statistics literature long before. But it was given this new name of machine learning, and that name has survived. I do think we have machines that learn, and I think that's pretty interesting. I don't think we have artificial intelligence yet. So that term arose earlier. Early 60s, late 50s. I think it was John McCarthy at MIT. Cybernetics was a term from that era as well, and that was an aspiration. It was kind of a philosopher's question. We have computers now. We have hardware and software. That's a new concept that, software could be like the mind and hardware could be like the brain. Could we, with that setup, mimic a human being? Wouldn't that be interesting to think about? Could that be possible? How would we do it? And so on. So that's an interesting aspiration, if you will. It's almost a scientific one and not so much a technological one. And I think to this day, it's still an interesting aspiration. But I don't think we're actually much further along than we were 40 years ago, and I think it'll be quite some time. And I'll talk about that as we go. Nonetheless, machine learning is real, and companies are using it all over the place. I think there's not a company that doesn't use it at some level. And whole new enterprises are emerging based on it. So I will talk about some of my thoughts in that regard. So the ideas are actually simple, but it's very far from being an engineering discipline of the kind that we would really have confidence in. So we're now, the early use of machine learning was in things like search engines or in speech recognition systems and so on. And if they failed in some sense, there was not a disaster. If a Google search engine, if I typed in a query and it gave me back answers which weren't very good, I'd just get frustrated, maybe annoyed, but no one would die. If you start building a medical prediction system that takes 100,000 patients per day, makes predictions about what's happening in their body, and then makes decisions about drugs and treatments, people will die if you do it badly, and they are, in fact, right now. If you build a transportation system for everybody on the planet, and it's done badly, you will have situations where there'll be traffic jams and ambulances can't get to hospitals and so on, and people will die. So I think of this somewhat like the field of building. So 3,000 years ago, people learned to build buildings and bridges and so on, a very creative use of materials. And it was very important. It allowed economies to be built, transportation networks set up, buildings were built. But there were disasters. Some of them fell down and people died, and there were crises. And eventually a field emerged. It's called civil engineering, which said things about, given this bit of land, the sandiness of the soil, this amount of wind, I can build a bridge which is guaranteed not to fall down. And we don't have anything like that for systems based on information and data and computing. Okay? We build them and we hope they'll work, and sometimes they don't work. All right? So in the financial world, there's occasionally been glitches where the glitches have been very, very painful and costly. But those are ones you can sort of easily perceive. If I start making bad predictions about medical treatments, it's going to take time for it to be perceived. And so we have serious issues at our hands. Okay, so let's get into this. So this slide is a lot of text here. I do want to spend a little time on these. This is actually historical ordering of some of the areas where machine learning was used in significant ways in industry. So I've already alluded to search. I was around in the mid-1990s when search engines started to get really good. And they got good based on taking in large amounts of data. So someone would type in a query and you'd give them back a certain list of pages, and you would see how long they dwelled on the page and how long before they clicked on something. It gave you an indication of how good that list of pages was. And so they had a machine learning algorithm which had parameters, and they were adjusted to make the better pages be higher and higher up in the page. And over many, many people's, millions of people using the system, it got to be better and better and better. To this day, machine learning is used critically in places of search of all kinds, including images and text and so on. The other one around that same period of time, which was really interesting and important, was fraud detection. In many countries, you have credit cards being used for transactions. Not all countries. China is a nice exception. The fraud rates historically have been around 3%. So 3% of all transactions with credit cards are fraudulent. And that rate is not great, but it is not so big that people are troubled by it. The system absorbs that level of fraud. But when companies started to have more and more volume and margins were thinner and thinner, it got more important to bring that rate down. All right, so you started to use data. You would collect a large amount of data. You would see, well, this transaction happened today in Cambridge. Someone used a credit card to buy falafel, but that person normally lives in Berkeley. Isn't this strange? Maybe I should flag that as fraudulent. Well, maybe you shouldn't, because it was actually not fraudulent. And if you flag that, it's going to be a red flag raised. It's going to be a false positive, and I will get annoyed that my credit card is not usable for a little while. So there's this huge issue of trying to find the boundary about where is a false positive and where is not, so that you can bring fraud rates down. So that was done rather successfully. And I remember going to Amazon back in the 1990s, late 1990s, and they were trying to build a system that brought fraud rates way much lower, because they were going to do massive scale purchases online. And they got their fraud rates down. It was an industry secret for a while, but around 0.001%. Okay? And that was just done with machine learning, taking in data, making predictions, and tuning the parameters until it got better and better and better over time. Another area which was important around that era was diagnostics, trying to figure out if your machines that you are building are about ready to break. So there are large numbers of machines in the shipping industry and other industries which cost millions of dollars to build and maintain. And if they break, there's a period of time when they're down and you lose huge amounts of money. So companies got very, very good at measuring the machines and trying to find out when the measurements you looked at were unusual, and flagging those things so that you brought in a technician at that moment and fixed it before it went out of whack. The airline industry also is extremely good at that, and that is all done with machine learning. Another one that is really, it sounds dull, but it's super important, logistics chain prediction. So again, Amazon was notably good at this. If you're Amazon and you're trying to sell 1 billion products to people, each one of those products is pretty complicated and it has many parts that were put together in some factory somewhere. And there had to be a whole supply chain behind that, a whole tree, right? And the branches on that tree are like ships moving through the ocean and planes flying through the air and so on. Things were accumulated in stages along that way in various factories. For it all to come together to make the product at the right time and have the right number of things in the factory near the city where people are buying it and have that all worked out is not just the magic of the market. It's actually logistics and planning. It's just actually algorithms. If there's a storm in the South Pacific, that's going to slow down certain boats, and that means certain things can't get through, and you better plan for that. All right? Otherwise, people are going to be trying to buy a certain iPhone or whatever, and there's not enough in stock, and it'll take weeks instead of days, and your company's in trouble. So they got to be extremely good at that, and other companies have observed that and have followed on. All right, the other thing that I guess I'm talking a lot about Amazon. It was the first machine learning company, really. In the 1990s, Jeff Bezos really understood the power of using data for everything, in not just AI, but kind of everything in the business cycle. So the other thing they did well was what are now called recommendation systems. So they realized that if you go on and buy a bunch of books, and someone else comes later and buys those same books, but not every one of the books that you buy, that you can propose the missing books to the person, and they will find that interesting. Oh, you seem to know something about me. Well, I don't know anything about you, but I know about somebody who seems to be very similar to you. That has had a huge effect on their bottom line. The number of people who buy extra books or movies is huge. Now I'm going to talk a little bit about where the limitations are on systems like that, and where the next, I think, business opportunity is. It's going to be in what I'm going to call two-way recommendation systems. Okay, so that's all. We're now, like about 2000. And after that, there's more things that look a little less businessy and a little more AI. Segmentation and personalization and text classification, cinema. So these are all talking about interfaces to people. What do people think about what I'm doing? What are their preferences? How do I sell them? How do I understand people? And that's very much where things have gone. Personalization is probably the biggest buzzword in Silicon Valley. Every company is trying to do a personalized version of some preceding technology. And all that means is that instead of taking all the data for all the people and putting it all together in one single algorithm, you take that same algorithm and you replicate it many times and let the data for each individual go into the algorithm. So you get a personalized model for every individual. How to do that well, though, at scales of billions of people, especially in places like China, is very much a big challenge. You have lots of data on some people, very little data on other people. And I would say these are still not solved problems, but are changing the world. Robot control. Robots are in many, many factories nowadays. You will start seeing robots in your home. There will be little robots that you'll interact with. The cell phone is not the end. The cell phone doesn't move around. It doesn't look at you. It doesn't know much about you. There are already companies that are building very interesting little robots that people are going to buy and put in their home, and that's going to be, those robots will learn from their surroundings. And then here's a maybe boring one, but bug detection. Huge economic problem. The number of bugs in software, it's really a huge drain on our economy. It's not that hard to build machine learning systems that watch the behavior of running programs, instrument a program, and when it crashes, learn from that and learn where the bugs are in the software. All right, so that is being done behind the scenes as well. All right, vision, speech, natural language, we'll talk more about that. And then risk modeling. Trying to make decisions about the risks out there, including the very big risks. If you're a company that sends ships across the ocean, if a ship goes down, that's many, many tens of millions of dollars. How do you insure things like that? And that sort of thing is going to become harder and harder. How do you insure things in society? And so taking data and learning from that is really critical. Okay, so I could go on, but I hope you give this is a little bit of the flavor, that every one of those things involves large data sets, computers, and put together with not so smart but decent algorithms allow you to do kind of sort of some amazing things. All right? None of them would you really call artificial intelligence. It's not as if you created a little humanoid that's doing all those things. It's just kind of good engineering with computers and data. All right, so where's that all going to go? The other thing I'm going to do is just give you some buzzwords, and this slide I'm not going to go through, but this is from 1999. I was teaching a class that was techniques, sort of a toolbox that you could use and go out in industry and sell yourself as a machine learning person. And really, these are the same topics that we're still teaching today. They really haven't changed. And so if you consult in machine learning, these are the kind of things you have to learn. This is, every one of those takes, a couple of months to learn about, and, this is the tool of the era. In the universities, this is more and more the kind of thing we're teaching even down in the freshman level classes. This is kind of the literacy for the 21st century. All right. So I'm not going to spend any time on that. I just wanted to kind of show that. That is a slide from 1999. Okay, so I'm not going to talk much about methodology today here. That would be a little bit dull. But I just do want to say something about how simple it is. Behind these algorithms are, you take in a data set. Think of like a database person, a table. There's rows and there's columns. And a row is like a data point, and it has many coordinates or many features or many attributes. And accompanying that data point is often a label saying that row is good. Some other row might be bad, and I have labeled rows in my table. And then I take that and put that into my machine learning system, and its job is to, for every one of those rows, make a prediction. Is it good or bad? And if it makes the correct prediction, nothing happens. If it makes a wrong prediction, that means some of the parameters were wrong, and they should be adjusted a tiny bit. So you do that with what's called gradient descent. You simply say, I want to have as smallest number of errors possible, so I'm going to go downhill by taking a step in a direction which makes the number of errors get a little smaller. Right? So it's really, really kind of very dumb stuff. Technically, in the world of convex optimization, you can do exciting sorts of applications, but they're limited, and the wave of interest right now is for systems that are non-convex. And it used to be thought those were kind of just hopeless. Mathematically, you couldn't do anything with them, and that's changed. Nowadays, we have lots of interesting theory and practice for non-convex optimization, and that's kind of what's happening. Now, the other technique, which is really critical in many of these systems, is to just very simple sampling and resampling. So when I resample from a data set, it's as if I'm getting multiple data sets from the world. The bootstrap in statistics is probably the most important version of this historically. But this notion of taking a data set and then looking at its possible randomness by sampling it again and again and again, that first of all matches with the dumb computer's ability to just sort of take data and do something simple over and over and over again and start to get an idea of fluctuations. This is an area which is as dumb as it sounds, is not widely deployed in machine learning. All right? People build a black box that takes in data, make a prediction, and they're just sort of done. I think if you're in the finance community, you know that's very dangerous. You need to have error bars around your predictions and have some idea of the uncertainty. And surprisingly, that's kind of, we don't have an engineering field yet. People don't do that. The systems are not built to do that, but they can be and need to be. The other kind of technology which is widely used are more control theoretic, dynamic programming or rollout. So all this means is that if I'm trying to play a game with nature, or if I'm trying to control a system, I'm going to have to put out a sequence of actions of some kind and find a good sequence of actions. So there's a branching tree of options, and at each step I'm going to have to figure out, should I go left or right, choose one of several options. And so many of these algorithms do the dumbest possible thing. They just try all branches, right? And in systems where you can simulate the world, you can do that billions and billions of times. So you probably have heard about the so-called success of AlphaGo, which, you know, beat the Go champion. And a lot has been made of that, that now the systems are so smart they can even win at Go. And humans, you know, have to spend years of their lives, and it's very, very hard and very challenging. Well, Go is a game where you can simulate it, all right? So the computer can do billions and billions of just try it out, rollouts, and see what works, and then remember that. So that's a lot of what these algorithms are. They're just dumb search, they're dumb stochastic gradient, and they're dumb rollout sort of things. And just surprisingly, that allows you to kind of mimic intelligent systems like humans, okay? But it's not all that intelligent. Okay, so let's talk a little bit more about, nonetheless, even though we don't have AI yet, what kind of things can we do? Well, these systems that are based on rollouts, and it's often called reinforcement learning, try out all the actions, maybe sequences of actions, and figure out what works. Well, you can't do that in the real world very easily, because the real world can't be simulated. It's too complicated, but there are things that can be simulated. So in games. And there, you know, games, I don't know if it's $1 trillion industry, but it's huge. And these games are very, very detailed, and they have simulators behind them. And you can have avatars that act in these environments, and they can try out all possible actions and become very, very smart in that limited environment. And that's interesting. If you're, I'm not a game player, but I can well imagine having an avatar that seems surprisingly smart is interesting. And so the gaming industry is well aware of this. Also, entertainment. In our lifetimes, entertainment has gone from, a stupid King Kong kind of, standing on top of the Empire State Building to just amazing, tigers that can, morph into dinosaurs or whatever, it's amazing. Again, many of the ideas behind that are extremely dumb and simple, and it's often 500 artists sitting there and changing the pixels from one thing to the next. Put together with some data analysis and machine learning, you can do lots and lots of things. So there it's easy to gather data because it's easy, again, to simulate and try things again and again and again. All right, so fine, it has a big impact on the world. I think the world will be full of more entertainment, more gaming. Also, every technology that allows humans to be more creative is interesting. Paints came along at some point and artists grabbed that. And, the ability to sculpt came along and so on. And a lot of these machine learning systems allow you to take in an image and morph it into interesting ways, or take in sounds and morph it in interesting ways. And just like synthesizers came around in my generation, these systems allow you to change signals in interesting ways, and that will be picked up by artists. So all that's pretty interesting. Financial services. So there are companies that don't just look at the world from a distance, but they actually record every transaction that someone does. So a credit card company, for example, is able to do that. In China right now, you have services like Alipay. So most people do all their transactions with their cell phone. And the company sitting behind that has all that data. So they'll have hundreds of transactions per person per day. All right? Now that's extremely good signal. You don't have to look at from a distance at what people, who clicked on what, and on ads and try to infer what they're interested in. Because you're watching what they buy. And from that, you can now make all kinds of offers to them, discounts for this and that, and start to target them in ways they probably don't mind. I mind it if you show me ridiculous ads that I'm not interested in. But if you show me something I happen to be a drummer, and you show me here's a beautiful Zildjian cymbal, and I'm going to give you a 50% discount on it, well, I'm interested. I'm in. So that will happen for all of us, and that is the next play for the financial services industry is to start to do that kind of consumer-facing services, recommendation systems for people based on having this extremely fine-grained data and doing that in a recommendation context. I could go on about that, but I think I'll get to some of that later. Another industry which is poised for AI-based innovation is home robotics. All right, so imagine a little robot about this high. There's one, I'm a consultant for a company called Gebo, which has just rolled one out this fall. You can go buy a Gebo. It has 6 degrees of freedom, and it can turn and orient, look at you, can talk to you like Alexa, Amazon's Echo product. But it can also take pictures. You can say, I'm going to have a party tonight. During the party, do you mind, whenever you see a clump of people together, taking a picture of them, and at the end of the night, send everybody all the pictures. I can say, Gebo, and it'll turn and look at me, and I can say, I'm going to leave the water running in the garden. When my wife comes home, can you tell her to turn off the water? It'll recognize her when she comes home, and it'll tell her that, and so on and so forth. So these kind of things are not super AI. They're fairly simple, but they're interesting and useful. And people will want to have things like this to some level in their home, and I think that'll happen in the next 10 years. So even though these are not like human beings, they can't interact with about everything that we would want to talk about and have a serious dialogue. Because they're in the home and they have a limited world to work with, they can learn about who's in this home typically, who's not typically in the home, what animals are in the home, and they can start to have a little bit of a notion about what our lives are like. So that is the entree to more serious AI. So in particular, if you want to interact with the computer using natural language, which I think is the most challenging problem in AI at this day, then you need to be in a context in which there's enough rich semantics that it's interesting, but you're not talking about the entire world. So when a company like Google or Facebook tries to build an AI system that seems intelligent, and its domain is the entire world, you can talk about anything, just like you can query Google about anything. That's hopeless, right? But if you're trying to talk about just what's happening in my home, it starts to get a little more hopeful. More generally and broadly, the notion of creating new markets that can connect consumers and producers. So an example of this are the transportation companies. Uber is an example, or Didi in China. If you want a transportation, you open up your cell phone, you say, here's where I am, or it knows already, here's where I want to go, and you're done. That request then goes to people in the cars, and they have their own cell phones with a different app. And the app, they're a producer, and you're the consumer. And a connection is made between you, and there's a pricing that happens in that moment, right? And then there's an allocation of some kind, so they don't have too many cars in this area, and so on. And so there's a whole dynamic system that's built there to do that. And that leads to liquidity, to flow. It's an interesting new economics. But that's just being done now for point-to-point transportation of individuals. What if you did that for everything? For restaurants, for healthcare, and so on and so forth. That you had producers and consumers being connected via a market, and they could all see each other's. They could bid, they could have pricing. We don't have that sort of thing yet, but I think that's where we're going. All right, and that'll all be based on on data analysis. All right, so I've already talked about these a little bit. Sort of in general, but let me say something a little bit more direct. These are 3 companies that I happen to be on their advisory boards or have consulted for. So I know something about what's happening behind the scenes here, and I want to make some of this more concrete by talking about their business model. United Masters it was announced in November. So music is a very, very interesting area for thinking about the commerce side of music. More music is being made now than ever before, by far. And it's because a laptop, you can open it up and you can make music. And very good music can be made by people who work at it on the weekends. They put their music on a site like SoundCloud in the US, at least. And more people are now listening to music than ever before on sites like that. Right? But there's no money being exchanged between those producers and those consumers to first order. No money at all. The record companies take a few artists and promote them, and they still make their money in the traditional way. But no money is being made in this market that's involving billions of people and hundreds of millions of producers. That just can't be, right? And it's deadening to the artists. The artists are not making any money, so they can't have a job as a musician. Even though they're making lots of beautiful music and people are listening to them, they should be able to have a job. That should be their job, but they can't. All right. So how do you fix that? Well, you can't just wait for the record companies to do it, just like you couldn't wait for the taxi companies to do it. So what you do is you say, look, I know who listens to who. I can go partner with Pandora, Spotify, YouTube, and so on. I can ask them for their data. I can say, for this emerging artist that no one's really heard of, well, it turns out 100,000 people are listening to that artist, and here they are. I can find out what cities they live in, right? And then I can give that artist a dashboard that says, here's where your community is, right? And so you've suddenly learned that for whatever reason, in Oxford, you're popular. So you go give a concert in Oxford and you make $25,000 because there's enough people there, maybe by word of mouth, whatever. Something happened, you're popular in Oxford, right? So then you learn that, you then go, when you make $25,000 and you do that 3 times a year, that's a salary, right? That's enough to live. You also can learn that among the people who listen to you, there's someone who happens to work in a finance firm. They must have a lot of money. You could offer to play at their wedding, right? You can offer to make them be a super fan and come backstage with you. Just give me $1,000 and I'll do this, right? And so now you don't have to, you do this for hundreds of thousands of artists, all right? You don't have to go sign them up and, and so on. You just make it available. You create a market. All right, and now goods and money can flow, and it's not on a pay-per-view system. It's basically just, if people show up at your concert, you make money. If you go to their wedding, you make money, and so on. Okay? So the company that does that, of course, takes a little bit of a cut. They don't take the traditional 50% cut that the record company would take. They take 15%. The 15% is not going to hurt the artist, but it's enough to make a lot of money. And this company, I believe, will make a lot of money. But more importantly, they will create a new way for people to have an exchange of a good, which has not been possible to date. And it has to be based all on data analysis. You have to figure out who are the artists which are emerging, and where's their audience, and how to connect them up, and how to let them visualize their market. Gebo is the company I just mentioned a minute ago. This is contextualized home robotics. So I do believe that within 10 years that most people will have one or more of this kind of entity, just like we all have a cell phone in our pocket, because we want to be able to interact with something which can move and orient and hear and see and so on. And then lastly in that list, I've now lost the picture. Oh, there it is. So Ant Financial. This is a company in China. They are the company behind Alipay. If you've been to China, everyone pays with their cell phone. And the first service they did, that's called Alipay. That was created because Jack Ma created the company Alibaba, sort of the Amazon of China, 10, 15 years ago. And in China, they didn't have to first order a credit card system. And so they've created this site now where you can go and buy goods, but no one can give them a credit card number. So how do you pay? People in China were paying with cash. They were banning everything with cash, including homes. So there's no credit card system. So they had to create a system. So they created Alipay, which is in the beginning an online system. And now you had 500 million people going to this site, created an account, and paying with this service Alipay. Suddenly you have extremely good transaction data, and you know something about the sound engineer helped us a little bit. There's a little high frequency. Yeah, thank you. I think you got it. So now you know a lot about 500 million people, and you know how creditworthy they are. So the next step was to say, from one day to the next, a little button appeared on people's cell phones saying, do you want a loan? If you want $1,000 or whatever, hit this button, and we will score you. Now, they didn't have a scoring system like FICO, so they created their own. And it was way better than FICO because it was based on data analysis, all right? And so if you got a little button there, you could get a loan and you could have $1,000 in your pocket from 1 minute to the next. And if you paid it off, this could happen again, right? So that is happening to this day in China. And I think in that sense, China has leapfrogged the West. I think there may be other areas, but this is the one where China is way ahead. Suddenly people who could never get a loan could not go to the bank and get a loan. That's less true here, but in China, much harder to go, just for an average person to get a loan. We're able to suddenly have this company provide loans to them at the scale that they're interested in. Okay, so it's microcredit done large. Now to do that, all behind that is data analysis. You could not do this by just building a system and platform. You had to analyze the data and learn about people. So that is going on. They call it the democratization of financial services, and I think this is interesting that it happened in China. When this company started doing this, of course, there was worry the government would clamp down in some way. But I think what happened is the government went to the banks and they said, "Are you folks worried about this?" And the bank said, "No, we don't care about those 500 million people. We just want to build big buildings and make the rich people richer." This is a capitalist society, right? Just like most hedge funds here in the UK and in the US, just make the rich people richer. And so Ant said, well, okay, fine, we'll just handle all the poor people. There's happened to be 500 million of them, so it's a good business model. And that has worked. The banks haven't really cared to first order, and this company has become huge. So if you haven't paid attention to that, pay attention to that. In the US, you still can't pay with your cell phone most places. But it's now possible, at least in San Francisco, to use Alipay if you're a Chinese person. That's their little way in. All right, but it's extremely interesting. Okay, so let me talk a little bit more about the main subject here, AI. What is it? Where did it come from? And what does it mean? So it emerged in the late 50s, early 60s. It really was this kind of armchair philosopher's notion of, can I create a robot that seems as smart as a human being? That's just an interesting thing to think about. How might I do that? And Alan Turing was one of the people, earlier than that, but one of the people who thought about this. And that has been the perspective which has led to the notion of AI that you see in the Terminator and other places. You see a smart robot that is not a human, but it seems as good as a human. Now that agenda or that aspiration has been around for 40 years, and we still don't really have anything like that. So using that same terminology of AI for the machine learning kind of things I've been talking about this entire talk is somewhat odd. because we don't have what was aimed to have, an intelligent entity sitting there as smart as a human being. So what seems to have happened instead is, first of all, what we might call IA, intelligence augmentation. So computers have been used to gather enormous amounts of data and provide it to humans, and the humans then you do intelligent things with it. My memory is getting worse and worse over the years. I can't remember the capital of Romania, for example. Oh, I can, it's Bucharest, but well, whatever. But I can't remember it, but if I needed it in a conversation, I could pull up my cell phone real quick, capital Romania, and I'd have it, and I would seem smart. I would seem to know the capital of every country in the world and the gross national product. And so I know all those things because it's at my fingertips. So in that sense, search engines have rendered all of us more intelligent because of them. It has augmented our intelligence. And similarly for translation, it's now possible to take in this microphone, I could speak in English. It could go into Google Translate, go over to Arabic, and then it could be put back out as speech, and Arabic would be coming through the speakers right now. That would be kind of poor Arabic in many ways, but nonetheless, it would be communicative. And so suddenly, I have the ability to speak any language, right? So my intelligence has been augmented. And that sort of thing is continuing. All around us, our intelligence, we are seeming smarter because of these things around us. All right, but I think even more broadly, what's happening is something I might want to call II, intelligent infrastructure. Uber is an example. It knows about routes. It's way better than the taxis. It knows where there's problems on the streets. It also knows about my preferences. It knows all kinds of things about me. And so around me, the world just got more intelligent. At least it's been to my will a little bit more. And that is happening in dwellings, and it's happening in urban planning situations. The world is just getting to be, in some sense, more intelligent. Internet of Things is kind of a buzzword that's often used for this thing. And so I believe this will continue. As your life goes on, you'll just notice around you that everything seems a little more intelligent. Speech recognition has become good enough that you can, nowadays at least, you can have your cell phone, turn your speech into text, and it's pretty good. It got more intelligent. Okay, so this is on the other hand wonderful. On the one hand, wonderful, and on the other hand, it's a disaster looming, because the algorithms that have been studied for this build a robot perspective, vision systems and speech systems and all, are really just glorified pattern recognition systems. They take in data, like I was saying, they adjust some parameters a little bit to make things better, hopefully, but there's not really much of a guarantee. And those same algorithms are the ones being used to build transportation systems and medical diagnostic systems and financial planning systems and so on and so forth. And they really weren't designed for that, but we have so much data that somehow they can be used for that. But we haven't thought this through at all, and there will be really disasters. And so here's just some of the technical issues that really haven't been thought about, but are critical when you start to deploy systems that are using AI or machine learning at scale out there in the infrastructure. So if I'm making multiple correlated decisions at massive scale, how do I control the errors? Right now, these robot kind of perspectives make you have each decision be done as a one-off thing. The robot makes a decision, and you have an algorithm that makes a good decision in that moment. But what if 100,000 people are making a decision about whether I should have breast surgery, because of cancerous growth in a breast, right? Well, you have now a huge correlation among people, and you can make one bad decision can percolate and cause a huge number of bad decisions. We've seen this kind of thing in polling. Trump got elected, amazingly, and I don't know anyone who would ever vote for Trump. All right, and all the polls made it clear no one's going to vote for Trump. And he won, right? Well, what happened is there was correlations that were not being modeled very well, and all the uncertainty and error bars were not taking into account those correlations. That sort of thing will continue to happen, and in domains other than politics, and get worse and worse. How to share data in competitive contexts. Lots of data is being collected. It's often being held privately and not being shared. And so probably the best example of this is cancer. We now can sequence individual cells and get the DNA out of an individual cell. And if you look at a tumor is a collection of cells. What happened in a tumor was that there was some kind of a mutation to a certain region that caused too much growth, and it didn't get stamped out somehow. And so for a little while, there was a whole bunch of cells that are clones of this original cell. They're all the same, and they have this same mutation. But because the mutation's bad, the DNA is getting kind of messed up. There's probably going to be another mutation, and another. And there may have been 4 or 5 mutations in a tumor. And so there's a bunch of cells that are this mutation, there's a bunch of others which are that mutation plus another one, and so on. So it's a little phylogenetic tree, all right? And if you go to somebody else's tumor over here, there might have been the same first branch, but then the branches are a little bit different, all right? Now, there's probably not billions of ways that a cell can get a tumor, can go bad, it can start to have its growth, probably hundreds. There's pathways, maybe dozens, but at most hundreds. If you knew each one of those pathways that could be broken, the part of the DNA and then the way that affected that pathway, you could probably find a drug which would work just on that pathway, all right? And so now what you need to do is collect all the data from all the tumors in the world, and that's feasible. You can now sequence them, and you can find out what exactly are the mutations in that particular tumor, right? And now go into the lab and create a robotic system that would take that tumor, clone it, zillions of times, and have the robot put every single drug known to humanity in each little vial and find out which drug affects that mutation or kills off that mutation. And so now you could learn for every possible mutation how to treat it. And now you can go to an individual patient and say, oh, you have those 4 mutations. I put in a cocktail of these 4 drugs, and bang, your tumor goes away. Right, so this is not science fiction. This is really doable. This is how cancer will eventually be solved, maybe even in our lifetime. But it's being blocked right now. Why? Because every hospital that has all these tumors will not share data with any other hospital. All right? Now, that's often for stupid political reasons and administrative reasons, but there also are business reasons why people won't share data. So fraud detection or intrusion detection, we're all aware of cybersecurity issues. Next week there will probably be some kind of an intrusion of some kind that some hacker in Russia worked out, and some particular bank or some particular entity will be the first to see it. They will start getting hit, right? If they were at that point to share their data with all the other entities around the world, a really good system could be built. Like an immune system could be built. If you would daily share all the fraud data from all of the banks and all the intrusion data from, you could build, which is simple machine learning algorithms, very, very good systems for detecting fraud and avoiding intrusions. But people won't share that. Why? Well, their lawyers tell them they shouldn't share it because that'll give away company secrets. Or competitive reasons. If I share my data with you and you have bad data, I have good data, your performance will come up where mine doesn't come up as much, so I lose relative to you. All right, well, these are game theoretic issues, and they are ones that can be worked out. The Nash equilibrium is not to have zero sharing. The Nash equilibrium must permit some amount of sharing, some loss of privacy, and all of our bottom lines come up, and I work out just how much. Cloud edge interactions at massive scale. This is completely unsolved. So we all know about the cloud. It's all the intelligence will be up in the cloud. But the cloud is too distant from the context, the semantics, the real world. And the cloud is too slow. So if I'm going to build self-driving cars, I do not have time to send the image up to the cloud, have it be processed, and come back down before I decide whether to turn left or turn right. All right? So you have this problem of some intelligence being in the devices and some intelligence being in the cloud, and the handoff and the synchronization of all that is really, really not worked out. Lots of discussion about fairness, quality, and diversity. If you just take existing data sets and you put them into a machine learning system, the machine learning system will just copy the behavior of that data set. And if there's biases and it's been collected in unfair ways, then that will be replicated in the machine learning system and probably augmented because the machine learning system will be used over and over again. The initial bias will get replicated. How do you fix that? How do you think about that? What are the legal issues that are involved there? And then all the cybersecurity and robustness issues are really, really hard to think about. So I think that self-driving cars will happen in our lifetime. I actually think probably in 10 years there'll be self-driving trucks in certain lanes of the highway. I don't think there'll be self-driving cars everywhere within 10 years, and it's really because of these robustness issues. Every day, every situation will be a little different than the previous ones. And some of that will be different enough that the car won't know what to do. And it'll take a lot of time to make these robust issues go away. Okay, so I hope you get us. Those are just some ones that I think are important that I could list, but in both the industry and academic community, these things, people are aware of them, but they don't work on these things yet enough because they haven't really deployed these things in systems that matter, i.e. systems where people lose their lives or amazing amounts of money. They've deployed these in things like search and shopping where, you know, it's annoying if it doesn't work well. All right, now, if we just go back to the iRobot perspective, even there's too much hype about what's been achieved. So in computer vision, we have a greater capability of recognizing images in visual scenes. All right, so it went from 70% up to like 90%. And this is the reason why there's so much hype about suddenly we have AI. All right, well, if you take those best performing systems, which are based on neural nets, they go up to 90%, but these are images on the internet where there's an image, there's an object typically in the middle that someone took a picture. If you take that exact same network and you go out in a scene like this, or you walk around the street and try to see what it recognizes, accuracy is about 20%. So we're at 20%, folks. We've not solved vision, right? And that's just talking about the objects in the scene. Humans, including my 5-year-old, my children, are way better are able to perceive a scene like this and understand the verbs in the scene. Who's looking at who hates who loves who's about to hit somebody, all the things that might happen next, all the reasoning about the scene that all of us do effortlessly. Our systems are just not able to do that at all. Okay, so we don't have even computer vision scene solved. Speech recognition, similarly, it's gotten pretty good. If I talk into a microphone, you can have it typed out in the English looks pretty good. But if there's lots of clutter, if it's in a real-world environment, that can go really, really south. But nonetheless, reasonably good. On the other hand, understanding the auditory world is we're far from able to do that. So if I close my eyes, I do understand that I'm in a big cavernous room. If I hit something there, I knock on it, I can tell whether it's wood or metal, and so on and so forth. So we have an understanding of the scene around us, which is not possible yet with our machines. But those are the ones that are somehow the most solved. Now we move into something which is just not solved at all, natural language processing. So people are, I think, overly impressed by translation systems. If I type in an English sentence into Google Translate nowadays, a French sentence will come out. I happen to speak French, and I notice that every sentence I put in, there's usually like roughly one error, and sometimes more errors. The error rate is about 90, or the correct rate is about 90% now. Well, 90% is not good if every sentence has 25 words in it. That means every sentence will have an error in it. So that's okay for just trying to build a simple business that takes in, just tries to, there's applications for that, right? Where it's bad translation, but it does the job, right? But if I'm trying to translate, really between human beings and communicate, if I'm trying to translate a novel, it's just not adequate. And I believe that in my lifetime, we're not going to get to the really translate like a human being. And then why? Well, these systems are not doing anything with semantics. They don't understand anything about the world. What they've done is taken in billions of English sentences and billions of French sentences, and they've learned to map from this sentence to this sentence with a machine learning parameter box. Okay? That's not how I translate from French to English or vice versa. All right? You speak to me in English a sentence, I understand what you're saying, and I take my understanding and I turn that into French. I do not map strings to strings. So it's going down a direction which might get to be reasonably good, but the real direction involves understanding the world around us, understanding the meaning of the words, and understanding how that relates to how I try to express myself. So that's just for translation. Areas in natural language that are more difficult include question answering, where I ask you, what's the second biggest city in England which is not near a river? That's something you could probably answer. That's hopeless. If you type that into any existing natural language system, it will not do well with that. And then dialogue. So to me, dialogue is the best example of something which is beyond our capabilities for the foreseeable future. So dialogue is I call up and I want to book a flight to Shanghai. all right? But I have my own constraints. I don't like to fly through Dubai, or I want to make sure that the flight is certain hours of the day, and then maybe while I'm thinking about this, I say, well, wait a minute, I need to stop over in Paris, and so on. The conversation can go in billions of different directions. At the end of that conversation, I want to arrive at a satisfactory outcome, that I got the flight I wanted, all right? So you have to understand a great deal about flights, about the world, about times, about constraints, and we're just not there at all right? That is just not doable. Now, there are chatbots that exist, and in fact, I do spend a lot of time in China these days, and people tell me about how great the chatbots are. So a chatbot is just a little entity. You can say something to it, it'll say something kind of cute back to you. So, if you're a teenage girl and you say something about some star, it'll say something about, oh, the star did this the other day, and so on and so forth. Right? But as soon as you say something it doesn't really understand, it'll just start talking about some other star, and it'll deflect your attention. And a couple of weeks later, you realize it has learned nothing about you. It doesn't know who your girlfriend or boyfriend is. It doesn't care. It doesn't know. And it's just a little thing which mimics intelligence without being intelligent. Robotics. We do have increasingly good industrial program robots, but robots that can interact with humans and operate autonomously is beyond still where we're able to be. It's hard to interact with humans because you need to understand something about humans. Right, now, what will be possible in 10 years? So I hate to do this kind of thing. I'm not a futurist. But the kind of things I talked about there will be present, at least in primitive form, I think, in 10 years. So there'll be dialogue systems which are in primitive form. They will exist because there's an economic incentive to do so. So if I have a call center where I sell refrigerators, and I have to staff it because some of the refrigerators don't work, they arrive at my home. I need to call somebody and say, it's not working. And they say, well, did you plug it in? Oh, yeah, I did, but is that light on or whatever? That costs a lot of money. And so you'd like to replace that with a computer, which can do a little bit of natural language reasoning, right? So something like a refrigerator, maybe it's going to be possible. For something like flights to Shanghai, no, it's not. But there's a big in-between. And a self-driving car is a robot. A self-piloting air taxi is a robot. Those will probably exist within 10 years, but again, in somewhat limited form. But these will still be very limited intelligences. You will not mistake these for a human being, even a child. They're going to be really, really dumb. So let me just say a little bit about why I think this. I've sort of said it a bit already, but let me try to dig in a little bit more. Humans are amazingly good with language because they have a rich understanding of the world. They can they can speak in an ironic voice. They can be funny. They can use metaphor. They can create an abstraction on the fly. Every word we use has got all kinds of rich shades of meaning that no one ever sat down and instructed us about. So before coming in here, I just picked up a newspaper and I said, let's take the first verb I come to, and then I'm going to get on the stage and say something about that verb. So the first word I saw was approach. So he approached somebody with a proposed deal. All right, what does that word approach mean? All right, well, nominally, the dumb robot thinks that I approach you when I walk up to you. I approach you, right? But that's not what's meant here. It's meant he approached me. Maybe we weren't even physically present. He sent me a note, but he was approaching me in the sense of trying to propose a deal to me in some way. So that's a very, very subtle notion. Approaching is now very, very abstract. But all of us understand all the shades. I won't go further with it, but we all understand all the shades, and no one ever sat down and told us that. There was never any labeled data to express all that semantics. We got it somehow, all right? Every word is like that, and if we have a sentence of 25 words, all the shades that are being expressed, all the relation to those words is amazing. So even think about a word like not. What does not mean, all right? If I say not David, what do I mean? Does that mean Rebecca? Or does that mean just not David? No, anybody else but David? Does it mean not him today, but maybe tomorrow somebody else? There's just billions of meanings just of that word not in front of a certain person's name. What about not tomorrow? All right, does that mean today? Does that mean never? Does that mean next week? It all depends on all the context and all the other words around that. All right, so I hope you appreciate we don't have labeled data for these things, and there's just no way we're going to ever collect enough labeled data to do these things. So we need more understanding of what does it mean, what are the semantics of natural language, and it's going to take decades, if not hundreds of years. We're also extremely good at abstractions. That's what computer science is kind of about humans come up with the right abstractions to express knowledge. If I tell you a brand new word right now, so I'm going to invent a word, let's call it a Gretsch. I don't think that exists in English. I say the Gretsch walked from Cambridge to London in a half an hour. You now suddenly know a lot about Gretches. You know they're animate. You know they're of a certain size. They can't be ant size because a half hour is not very, so they're a certain size. And I could probably ask you lots of other questions about Gretches now. And you could answer them plausibly. You could even give a probability statement. Right? Our current neural nets and machine learning systems, this is not how they work at all. You add one data point about a Gretsch to the big data training data set for this thing, it's going to change the parameters a tiny amount, and it's learned nothing about Gretches. It has to have hundreds of thousands of trials to learn. Okay, so I think that what we will have is AI systems that seem like children who know an amazing number of facts. They know the capital of Romania, and they know all kinds of other facts, but they still are amazingly stupid. Okay, they can't string it together and think and have a long number of thoughts. Okay, so we will have nothing like superhuman AI. We will not have a singularity in our lifetime. You know, Elon Musk is full of it, as is our friend Stephen Hawking. So I do need to say that because it's amazing how much airplay they're getting and how much the newspapers are writing about what they think. Stephen Hawking, God bless him, brilliant man, but he is not an AI person. He's never tried to build a natural language system or a vision system. He has no clue about what's involved there. And so he's extrapolating and imagining something which is just very, very implausible. Similarly, Elon Musk, he doesn't have any idea. I said that in China about Stephen Hawking, that he didn't know what he was talking about or something. And the Chinese love to blog more even than Western. So there was a blog, people started writing that Michael Jordan said that Stephen Hawking is a layman. And I don't know why it got translated to that layman. But then it got picked up in the Western press a little bit about Michael Jordan says that Stephen Hawking is an idiot or whatever. And this made it back to my mother, who wrote to me and says, you know, I see you've been in China. Aren't you getting a little full of yourself? Yeah. So I read The Economist, I read other places, and most of the things I read about AI and all are fanciful science fiction, but they're not the real problems. And they're not about the fact that a lot of these systems won't work, they're going to cause disasters, they're going to cause problems, and we can't do the kind of simple natural language things that you think we can do. We're not going to have systems that are intelligent and have agency and want to kill off all humans. Okay? We are going to have other kind of problems, and let me say a little bit about it. What is worth worrying about? Well, I've already alluded to this, but AI systems that seem smart because they know an amazing number of facts, they can beat you at Go and chess and whatever, so they seem incredibly smart, but they actually aren't smart at all. And if you ask them for something serious, like about should I have an operation on my heart because of, you know, et cetera, and they say, yes, you should. Well, they probably don't know what they're talking about. The loss of jobs and incomes by large numbers of people. So even though we're not going to have dialogue systems that are as good as a human in our lifetimes, we will have systems that can pick up the phone and dialogue with you a little bit about your broken refrigerator until you maybe get impatient, or you said something about, oh, there's funny marks on here that my son seems to have, you know, carved his initials. The system won't understand that. But short of that, it'll help you. So you'll displace large numbers of people out of the service sectors. These people have already been displaced out of other jobs. Now they're being displaced out of the service sector. Where are they going to go? And again, normally in previous industrial revolutions, you'd have 30 years to move, and this is happening like on a 5 or 10 year time scale. So that's very serious. Further disparities in wealth and lifestyle if knowledge is not diffused. Again, these are simple systems, but it is, requires money to build them and time and energy and all to do them well. And so that needs to be diffused. So I do go around the world a lot. I do go to China and other places and make sure that everybody hears about all these things. I don't want it to be concentrated. And then there are bad people out there who have bad intentions, and AI and machine learning ideas have a lot of power, and people will find clever ways to use that power to bad uses, and we have to worry about that. Okay, so underlying this technology, again, I've emphasized a little bit, but let's say it a little bit even more clearly. Really, it's just machine learning, which is these simple kind of algorithms that take in data and make small adjustments to internal parameters and state. But also the fact that we can put data and computing on very big, large computing platforms allows us to, is a major part of the underlying technology. And then the interaction between humans and computers. So when I had my first computer, the interaction was very, very limited. I could type, and I had to put things in a certain syntax and so on and so forth. Well, that's kind of starting to go away. That boundary is being broken, and so there'll be a symbiosis with our systems more and more. And when that happens, we have to have more understanding of economic models. Things have to be able to priced. I have to interact with humans in a game theoretic way. That's really the way the systems have got to work, and there's much to do there. Okay, so I think I'm going to briefly just say something a little more on the kind of what do we actually do as academics. I tend to work more on mathematical theoretical concepts because I think there's a lot of them missing. But there's a project I just wanted to mention at Berkeley that reflects some of our ongoing work to try to build scalable systems. There was a lab that preceded what's called the RISE lab. It's called the AMP lab. And this was an interesting collaboration. Mike Franklin is a database researcher. I'm machine learning, and Jan Stojka is a networking researcher. And we felt that those three expertises this is like 7 years ago. Putting them together was interesting. And so a lot of products came out of this. Spark is rather well known. It's probably the most widely used data processing software out there. And these others are maybe a little less well known, but I was involved in several of these and I'm proud of them. They are widely used too in industry. And what was interesting about this was that in that same era that we were building all this software that has gotten used, all the big companies were also putting out software packages to do big scale data analysis. So IBM famously had one, Microsoft had one, and so on, Google. Those didn't get used, all right? They had no pickup, there were no customers, roughly. Whereas this academic group built products that everybody uses. And that really is an important part of the modern technology spirit, which is that no one trusts the big companies anymore to buy into their software. If you use the IBM product, you're now bought into the IBM system. And if they change something you have no control over, you're sunk. If they make you pay twice as much, there's not much you can say. But an academic project, which will never ask money from anybody, is being done in an open source way, people will trust, and therefore they will build their whole ecosystem around that. And that is a fascinating economic fact. So we moved on from the AMP lab to RISE lab. It's more about real-time decisions and live data. So it's more about, like in your finance world, it's that sort of style of thinking. A lot more control theory kind of ideas are coming into play, and it's less about just big batches of data and processing them. So we're targeting these kind of applications, let's call them AI. And so the project I want to highlight really briefly here is called Ray. In some sense, it's not call it a replacement for Spark, but it does some things that Spark doesn't do very well. It does them much better. It has a microkernel functionality, and it targets systems where there's a closed loop, where you have a policy, you act on the world gives you some feedback, and you then adjust things and keep going. So it's more of a control theoretic sort of system. It goes beyond supervised learning to allow these broader kind of reinforcement learning systems. And it is able to stream data from many different kinds of heterogeneous processors and in real time and spawn off little processes that asynchronously handle little bits of tasks. So it's very different from the Spark and Hadoop and so on kind of model where you have block synchronous data processing. A huge block of data comes in, it gets farmed out to a whole bunch of processors, they all work in parallel, and then you wait for them all to finish and you bring them back together. That's called map-reduce paradigm. So that paradigm has been very important, but it's run its day. And so many of these modern systems have little tiny tasks that run for a certain amount of time, other tasks can run much longer, and you need to mix those in an overall system. Okay, so these rollouts in particular example, if I'm trying to figure out a sequence of actions to do, I'm going to try sort of all possible sequences, or many of them, in a Monte Carlo style. And very often it's the case that this particular path here, I might very quickly find out it's a bad idea. It doesn't work at all. And some other path, it takes me much longer to find out that it's maybe not such a bad idea for a long time, and eventually a bad idea. And so this process will run and it'll end. And I don't want to then wait till this other process finishes. That'll slow things down. And so Ray on some problems is about an order of magnitude faster than Spark because of this ability to have different heterogeneous tasks. This is an existing system. I'm going to show you, I'm going to skip through some slides. I kind of want to finish. This is an architectural diagram. I don't want to get into details here, but you'll see a lot about scheduling. So this takes scheduling as a first-class citizen. All the local processors have their local schedulers, and they communicate with a global scheduler and their object table. So behind the scenes, a lot of work is being done so that a person can just program willy-nilly and have a distributed system set up to solve these rollout kinds of situations. So I'm going to give you a little example here and finish. This is the problem of learning to run. So here we have a little robot here, if you will. It's a simulator robot, but it's called MuchoGo, and it's a little robot that has about 60 degrees of freedom. So not that different from a human body. And it's controlled not by moving each one of those things in a stick figure sense, but by each one of those joints has a muscle around it. And you pull on the muscle, you exert a force. So it's, again, very much like a human. Now, why would you want to build that sort of thing? Well, because it's very hard to build a graphic system that can create a human gait. Like when I walk, there's all this kind of natural movement and oscillation. It looks natural. That's very hard to create in a computer by graphics people. And to this day, like a movie like Avatar, where these people were swinging from the trees, and not people, but these avatars, that was done with a green screen and real humans running around on pieces of pipe and jumping. And then the graphics people, 500 of them, would sit and move the pixels around to turn those humans into avatars. So extremely dumb. So it's an interesting economic model to be able to how to create natural-looking human motion. All right. So this is a perfect example of dumb parallelism with reinforcement learning. Here's a little bit of Python code that just runs a simulator again and again and tries things out. So I'm not getting into details, but just trust me, this is about as dumb as you can be. Try out a bunch of actions in parallel. This step down here then will just do that for many, many processors, try out many, many trajectories. Okay? Ray adds a few annotators here. Ray remote says, I'm going to do this over many processors. And then Ray wait and Ray get allow you to query these remote processors. And when they finish, they will tell you the answer. All right, so you really write Python code, and you don't have to worry about distributed systems thinking at all. OK, so I'm going to show you results from this, and then I'm going to finish. This is this robot. So we have 60 degrees of freedom. Imagine a marionette. And you're supposed to get the marionette to try to run, okay? And but you have 60 wires to pull on, and you're not actually pulling on the joints. You're pulling on muscles that pull on the joints. So you can imagine that's hard. And a control theorist would not know how to do this. This is just way beyond whether modern control theory is. So how do we do this? Well, we just say, robot, if you manage to move to the left, or I guess to the right, that's good. If you don't manage to move to the right, that's bad. That's the only information we're giving it, okay? So let's see how well it does. All right, so in iteration 20, it's not doing very well at all. 60 iterations, it starts to maybe do something, not still very well. Here at 80, it's found some little policy that allows some motion to occur. All right, there's 100. Still not too good. Now at 200, it seems to have discovered how to balance itself and make forward motion. So not too bad. And this is at 500, and at this point, it is really running. Now, it's got this funny thing with its arms flailing like there. But that has a little bit of natural look to it, and that's only after 5 iterations. So it starts to feel not so far off from like a human who's learning to run, or a horse or whatever. And if you go to about 1,000 iterations, those arms come forward. And so this is done with very little training information. So this is kind of an example. I wouldn't say this is changing the world. But this is an example of the kind of things you can do just by trying things out huge numbers of times, as is AlphaGo. OK, importantly, this is open source. And so we put these things out there, and people around the world are contributing to this system. And that is really one of the fun things about this new world that we're in, is that we all do it cooperatively together. All right, so I'm going to finish there. I don't think if I had, yes, let me just leave up this slide as a last one here. So those who are in my field, who are machine learning people, this is my favorite list of things to kind of keep in mind to be working on. But all kinds of things about notions of uncertainty, about doing causal inference, about explanatory systems, about systems that have long-term goals, robustness, and so on. These are the kind of things that I think are going to take not a few years, but decades to really build a serious engineering systems field that takes in data, uses computing, and use it to solve real-world problems to somehow make humans' lives better. And that's really what this is about. This is not really the gold rush where it's just, here's the opportunity, let's all make a lot of money. That's good, but it's really about, here are tools that can change human lives for the better. It is that kind of technology. And when I go around, especially talk to younger people, you know, US, UK, Europe, China, that's what they seem to be interested in. They're not just interested in a company that makes money. They're really interested in what can I do that's going to be really, that people really want to use and will make their lives better. And that to me is exciting. It's a technology that does engage people and people's aspirations. Data is about people, typically. And everybody has their own data they're interested in because there's some phenomena in the world that they're interested in, often a public policy question or something. And I think that's wonderfully exciting. It's technology that touches on people. Okay, so I'm finished. Thank you very much. I won't say any other summary. I've just kind of gone through some opinions, got a little sense, I hope, of not the technical details, but about what it all means, and then I'm happy to talk, answer as many questions as you want to pose. Thank you. All right.
Thanks very much. So I'm going to put some of the questions from the audience to you now.
Okay. Why don't you stand up so people can see you? It's a little more natural.
So you mentioned that some of the underlying statistical procedures haven't changed much in the last 30, 40 years that people using machine learning. Is this a surprising thing? And do you expect the underlying methodology to improve in order for true AI to emerge?
So I think that the methods have not evolved that much, but computing and data sets have evolved an enormous amount. And so I think the finance industry is a good example of, you know, already 10 or 15 years ago, there were some pretty big data sets. And so people were using these kind of methods very early on in the finance industry. But I've noticed in the last 4 or 5 years that even more data has become available and more concern about very large-scale computing has become part of the story. So I think it's less about the algorithms and more about just that. That's the phenomenon we're living through right now. But who cares about AI, really? Why do we want to build another human being? Right? We have enough human beings. So I think it's these kind of things I had on a slide a minute ago, just about the serious engineering, boring stuff of getting scalable, robust systems to happen. And for that, yeah, we need new ideas, but they don't seem impossible to come up with. And somehow, good engineers will come up with this. And someone who's focused on the Turing kind of problem of how do we create an artificial human, I think I don't have any idea how to do that. And I think we're very far from that, and I'm just not interested, frankly.
Okay, thanks. Do you think that the huge amounts of data required to train ML models creates perverse incentives for invasions of the personal data of customers? And should there be a code of ethics for ML practice?
There should be lots of codes of ethics, yes. Ethics are critical. How do I collect the data, from who, what's representative, and so on. I don't think you necessarily have to have huge amounts of data. If you have good data and they're targeted for particular purposes, it doesn't have to be the biggest players are the ones who win. It's putting together data in smart ways and getting the right data. But yeah, there's huge numbers of sampling issues. It's very easy to collect a data set and imagine it was collected unbiased way. And it almost certainly was collected in a very biased way, reflecting all kinds of built-in biases and just measurement biases and so on. And so a team that works on this, I think any industry that's doing serious data science, machine learning should have like 500 people devoted to it. And a good half of them should be really thinking about the human consequences of everything they're doing, including the ethical issues, the ownership issues, the privacy issues, and so on. So companies have been trying to get by on the cheap in some ways, and I think that they've kind of learned their lesson.
Thanks. Do you think, how have recent developments in our understanding of the human brain improved machine learning, if at all? Is that our best route to improve machine learning?
Yeah, so I'm going to say something a bit provocative here, which is I don't think we have any idea how the human brain works. And so I don't think there have been recent developments in understanding the brain. I'm just not aware. Neural nets are just layers of little processors. Well, we have layers of transistors. We have layers in control systems. We have layers of all kinds. We didn't need the notion that the brain might have layers and connections to have that idea. And moreover, a neuron in the brain is like very, very complicated. It's got a dendritic tree that's this bushy thing with tens of thousands of branches and all kinds of electrical signals and chemical signals running around. And it's still not known how memory works, just even how do I just retain a memory? Where is the memory? In a computer we know, in the brain we have any ideas. So I just we're not there. I think that's the problem in hundreds of years from now. We can't measure enough about the brain to really understand it. Even in a nematode, it's got it's a little worm. There's 1,000 cells, and so the entire diagram is known, but it's still not known how the nematode works. It's not understood. So no, I don't think the brain has helped it at all.
Okay, thanks. How do you avoid database systems adversely changing users' behavior? For example, echo chambers built in social media.
Oh yeah, no, I think that's an unsolved problem and a very, very important one. I think those of us in technology have just got to be honest that we were shocked and surprised by the fake news, phenomena and the anonymity problems. So I'm not on social media at all anymore. I did a little bit of dabbling, but you see the worst of human beings on these things. You see the anonymity leading to comment sections which are just horrific. You see people being attacked, ad hominem and so on. So that is a huge problem that came up with this. And so I think that finally, like the Mark Zuckerbergs of the world are realizing what they've wrought and are starting to take it a little more seriously, but it was amazing how long it took for them to take it seriously. So every technology comes with, there's phase, I'm sure the steam engine, there were explosions, there were problems, there, displacements and so on, and so people had to fix those things. But this is, social media is very broken for many purposes. And so it's not just a technology problem, it's probably anonymity is not a good idea. You need to have people have identities, and those identities have to have reputations, and those have got to be built up. Probably too much privacy is not a good thing. Some amount of some control over it is good. Probably also people need to be paid. If you collect my data for certain purposes, I should know that, and there should be more transparency, and I should get paid if you use it in a certain way. It should be a human, understandable, transparent economic system that we build, and not just this open-ended free-for-all. And the echo chamber, I don't know. I'm not a sociologist, but there is more news out there if you go for it than ever before. It's just there's no reputation systems, and there needs to be other layers around it, but not just a technology problem.
So there's a question about NLP here. What do you think are the major challenges to understand semantics in NLP? And I guess you've answered this to some extent already, but are researchers in neuroscience helping the development there at all?
So I think that NLP's semantics is going to take a long time, just like I alluded to. A word like approach or a word like not has its own semantics, which is quite complicated. So I think this needs to start out by developing the right kind of language to talk about these things, and it's not just neural nets. It's got to be something a little bit more like a first-order language where you have notions of relations and quantifiers and so on. And then I think this has got to be built in realistic verticals. So maybe travel is too complicated, but something between refrigerators and travel. You have to be in a domain where there's entities and actors and they have relationships among them, and you can express some of that in structures and then use data to help craft variability around that. So what neural nets are very good at, like in the vision domains, is I can have your face in a billion different versions of it, and I can recognize you. It kind of gets rid of the extraneous noise. Well, there's that same kind of thing in English, in languages too. I use, I can say the same sentence in 45 different ways, and those differences don't matter for the semantics, and a neural net can get rid of some of that, presumably. That's what it'd be good at. But to isolate the abstractions that are being talked about and how they relate to the world, that is not just collect data and mimic something out there. That's try to think about what data structures are needed, what relational structures are needed and so on. So it's partly just old-fashioned AI. And I think that I resent right now that the neural net wave and the deep learning wave has become so predominant that people say, well, that's the way to go. You just collect data and intelligence will work itself out. And that's just not true. I don't believe it. You can mimic intelligence at some level. You can mimic, natural language translation, you can mimic some amount of it, but you'll not get to the level of human fluency. And so we have to think about what else was needed.
Thanks. So there's a question here from someone who works in higher education. And they say, how well do you think our education systems are preparing students for the impact of AI? Do you have any case studies of how this is being done well?
So I missed a little bit of that. So can you say it again?
It says, I work in higher education. How well do you think our education systems are preparing students for the impacts of AI? And do you have any case studies of how this is being done well?
I have a narrow answer to that, which is that I think we've been too funneled into the old disciplines of 100 years ago. And so minimally, you should have a very good understanding of computer science and statistics together. And very few people really have that breadth of understanding. It's kind of a graduate level thing to achieve, and even there. So I'm in both departments, and I see my computer science faculty colleagues having essentially zero understanding of statistics. And I see my stat colleagues having zero understanding of computer science, even to this day. The students I start to see, they're able to do both. But so we were working on curricula that merge them. When you teach Python, you also teach it with, do an A/B test and make an inferential statement in Python as part of at the freshman level. And students like this kind of thing. They like working with data. They like making inferences. And so we have a class at Berkeley which has it's being taught at the freshman level with no math, but it uses the computer to do things like bootstrap and A/B test and permutation test, kind of machinery in statistics that doesn't need math, but uses the computer to resample. And we have 1,000 students per semester, so 2,000 students per year taking this class at the freshman level, and it's not a requirement. It's just because their word of mouth has gotten that this is really interesting and allows you to work with real data sets and so on. So I think there's a awareness. So students in the U.S., there's a lot going bad in the U.S. these days, politics, et cetera. But the students are not going into law or business anymore. They're all going into computer science and statistics and economics. So I think that's really, really interesting. They get it, that somehow this is the future. So we got to help provide the training.
Thank you. So we're pretty much out of time. I just have one very quick question of my own. So you talked about all the hype in machine learning and AI. Do you foresee another AI winter, or are you optimistic about the future over the next decade?
Good question. I think a lot of these, even the term AI winter is a bit of a hype. I mean, I was around in the so-called winters. It just meant that certain professors got less grant money. Who cares? It's a lot of this buzz and hype and just discussion. It's kind of titillating to talk about. But, it didn't matter on the ground. And so this wave of there's a lot of data and there's lots of problems that can be solved with it. You can make predictions about the world. You can build better economic systems, better systems for helping people. That's not going away. That's all extremely real. In this talk of argument, let's not even call that AI. Let's just call it something else. So that's a $1 trillion industry, and I think that's fascinating. But if you watch the media and care about it, you will see terms like, AI will, in 5 years, well, that AI failed. They will say that, I guarantee you. And that'll lead to less funding or whatever, but who cares? There are all kinds of problems, and so there's like 500 people in the room tonight. When I go to China and give a talk, I get 5,000 because everybody there really this is what they want to be doing, and so the humans are gravitating towards using computers in new ways and data. So it's not going away. But somehow journalism has got to change as well. So journalism is very, very educated down. It's using old ideas for new problems, and so they have to hype things to get readers, I think. They've lost their readership, so there's an incentive to hype things, and that's what they are doing. So even places, reputable places like The Economist, New York Times, and so on, most of the stuff you read about AI is just kind of junky, and it's trying to tell a story which is not the meaningful story. So I'm just not worried about it too much.
Thanks a lot.
All right, thank you.
That's it.